Hi, welcome to the Chemistry Department of the Sixth Form College. I hope this short presentation gives you an idea of what it'd be like to come and study A-level chemistry with us. We offer the OCR B Chemistry course, which I think is more interesting because it allows you to meet chemistry in the context of ideas, and we revisit topics as you go through. But the basic chemistry we cover is the same as on any other A-level course. You're probably worried about been a long time since you've done any chemistry. Well, we start the course with a unit called Elements of Life, and in the context of thinking about the universe, then we will go over lots of the ideas that you met at GCSE to reinforce them, to check that you understood them. We'll start by practicing chemical equations. We'll tell you again what the mole is and how you can use it to find calculations of how much substances are going to be made. We'll look at some of the parts of the periodic table, how they behave, how they bond together, and we'll try and work out why molecules are a certain shape. Why is it that water is V-shaped and yet carbon dioxide is linear? Does it matter? Yes, because water is a liquid and carbon dioxide is the gas. We wouldn't be alive if water was a gas. We'll then go on to a topic called developing fuels that helps us think about why some molecules release energy when they combust, how much energy they release. We'll talk about some of the pollutants that they produce and the problems that they cause. And then we'll look at some organic chemistry, carbon compounds, how they form, why certain molecules behave in the way they do. You might remember the test for alkenes that they decolorise bromine water. Well, why? Why does that bromine choose to go to that carbon? So in this unit, we'll talk about the group 7 elements and how they behave, but we'll also look at redox reactions. What actually is oxidation? What does it mean? How do we write equations for it? An equilibria, you might have heard of it, but where is an equilibria? What does that mean in terms of how much product we can actually make in a chemical reaction? In this topic, we learn about free radicals and how they behave. They're highly reactive because they've got unpaired electrons. And we relate it to the ozone layer that protects us from that high frequency UV. But as some of you know, the ozone layer has been damaged by some molecules. What's caused it to be damaged and why? And from that we'll look at the rates of chemical reactions. Why is it some reactions are very fast? Why are some slow? And we'll relate that to intermolecular forces. Why are some molecules gaseous, some solid? What forces hold molecules together? This is the last unit in the first year, and we learn much more about organic chemistry, why some groups behave as they do. We apply that to the molecule aspirin, what the groups there, and how do we know? How can we use techniques to find out what bonds molecules have and how they're going to behave? So we learn about infrared spectroscopy, mass spectrometry, and make some aspirin, test if it's pure, and do a bit of research on how to make aspirin. The following slides show you some of the topics that we meet in the second year of the course, where we build on the concepts of the first year and are able to see many more applications of the techniques that you've learnt. The Polymers and Life unit in the second year has quite wide overlaps with the biology A-level. We learn more about the chemistry of biological molecules, about amino acids and how they form proteins. And we look at the chemical structure of biological molecules like DNA. We also look at new spectroscopic techniques called nuclear magnetic resonance that allow us to understand more about the shapes of molecules and how we know which atoms are bonded to which. The oceans is a more mathematical topic. We look at pH and find that it's not just a random number, but actually a measure of the concentration of hydrogen ions in a solution. We look at something called entropy, which is a measure of disorder in the universe. And we learn more about enthalpy changes, why molecules are insoluble, but why some ionic compounds dissolve and others don't. In the developing metals unit, we learn more about the transition metals, which have very interesting chemistry. They can form lots of different oxidation states. They're coloured. But why are they coloured? And how is it that we can create a voltage from chemicals? How does a cell work? The last unit of the course, Colour by Design, brings together all the organic chemistry we've met over the 2 years. It enabled us to look at the structures of dye molecules and how they behave and how you can make them. But we're also able to develop stage synthesis of reactions. So for instance, we can look at how you start with a simple molecule called benzene and can turn it into ibuprofen in a series of steps. So at the end of the 2 years, there are 3 exams, which can be on any area of the syllabus, including some multiple choice questions and an advance notice article that you get asked questions about on paper 2. Also, there's a specific paper that relates to practical chemistry and practical chemistry techniques. And we encourage students who want to take part in the Chemistry Olympiad competition and also in the Cambridge Lower 6 Chemistry Challenge. It gives them an opportunity to really stretch and challenge themselves. You'll have access to a textbook called Caboodle, where it follows the course. You can add your notes to it. It has questions in with some answers at the back that allows you to follow the course as you go along. Over the 2 years of the course, you'll do 12 different practicals that will count towards a practical endorsement certificate. You'll get that alongside your A-level at the end, and it's a range of different practicals covering all the sort of techniques and theory that we'll cover in the course. Should you be taking A-level chemistry? Well, one of the key factors we find is people's ability at maths. Can you rearrange an equation? Do you understand what ratios? Are confident using standard form and number of significant figures? We'll go on to look at logarithms in the second year. And here's an example of a sort of question you might do where you need to follow step by step to come to a conclusion and showing you're working. So in order to study A-level chemistry, you need a minimum of a grade 6 in Maths GCSE. The maths really gives us an indication of how people are being able to apply knowledge and solve problems. CGP produced 2 books that you might find useful. The Head Start to AS Chemistry Guide is for all courses and would be useful to look at before you come. It'll refresh your knowledge of GCSE chemistry, the reactions and the calculations that the course includes. The revision guide is specifically for the OCR B course that we offer at college and is strongly recommended. It would be a good idea to purchase it before arriving at college. We usually offer students an opportunity to buy it once they arrive, but if you've got it already, then you'll be prepared. So what do people who study A-level chemistry go on to do? Well, it's very wide-ranging. Many people choose it because they know chemistry is required for careers in medicine, but it also leads to a wide variety of other choices, including subjects like material science or environmental science that you might not have thought of. The Royal Society of Chemistry has produced a couple of videos on options that you can take from chemistry A-level. And another one about job profiles, where people describe the sort of job they're doing that involves A-level chemistry. I hope you find them useful. Here's a sort of question that you might be thinking about if you're taking A-level chemistry. If you want to have a guess before the answer appears, pause the video here, and on the next slide, they'll show you how you would calculate how many molecules of water there actually are in a cup of tea. So this calculation shows that in a cup of tea there are about 8.4 million molecules of water. Overwhelming number. And here's an organic chemistry puzzle for you. How many molecules have 4 carbon atoms, 10 hydrogen atoms and 1 oxygen? You probably won't have met this before, but every carbon has 4 bonds, every oxygen has 2, and hydrogen has 1. So you could try drawing out how many different combinations of C4H10O you can come up with. There are 7. Pause the video before you see the answers. So these are the 7 molecules that have the formula C4H10O, known as isomers. The first 4 are all alcohols because they contain an OH group, but the last 3 are known as ethers. They're chemically quite different to alcohols. The formulae on the right are known as skeletal formula that just show you the backbone of the molecule.